What's up, everybody? It's Dan from SageMathTutoring.com, and I'm back with another video. This one has to do with some relatively high-level calculus concept stuff. There's a couple problems. I just worked with a student. There was a couple problems where the answer on the answer sheet sort of baffled me in the moment. So I kind of did a little research to figure out and get to the bottom of what's going on with these questions. Basically, they're true-false questions. So anyway, let's get started. There are 5 total questions that we're going to be looking at in this video. All right, so for this one, if f has an absolute maximum value at c, then f prime of c equals 0. So the answer to that is false. And actually, a counterexample would be nice. A nice counterexample would be something like, I don't know, maybe even this function, where you could say negative absolute value of x, and that would be this right here, okay? Now that goes sort of down forever, and it is the case that it has an absolute maximum at 0. Here it is, right? So the point 0, 0 is the vertex, and the absolute maximum would be 0 because that's like literally the highest y value in the whole graph. However, this is not differentiable. This would be an example of a function that's not differentiable at that particular point. So therefore, this whole idea of like, oh, the derivative of f of c equals 0, well, there is no derivative, okay? So this absolute value function would be a great counterexample to this claim. So this one is false. Now, for my student who I just worked with, just know that, a function that has like a corner like that it's not differentiable at that x value. It's also the case that if you have a function where there's like a break like that, and maybe that break occurs at x equals 1, so that gap right there means that this particular function is also not differentiable at x equals 1. And then there's another scenario where you could have a function that kind of looks like this, where it's almost as though there's like a vertical line being formed there. It's not the case that there's a vertical line, but if you zoom in and create a tangent line, then that tangent line itself would be vertical there, okay? So in other words, if you have a fly that's flying this trajectory, there is this like one split second moment where it's going straight down. And the fact that the tangent line is perfectly vertical means that the slope is undefined, which means that this graph is not differentiable at this point because it results in an undefined slope right there, okay? And to be clear, let's say that x value right there, this x value is like 3. Basically what I'm saying is that the derivative of this function at 3 is undefined. Okay, so that's a scenario where it's not differentiable at x equals 3. Okay, so hopefully that makes sense. Now this is not completely related to this. This graph is a great counterexample to this, though. But this is sort of the big picture of when graphs are not actually differentiable. And whenever you have a corner, then you're dealing with a graph that's not differentiable right there. And also you might see things like that, you know what I mean? Anytime you have like a sharp point or whatever, it's not differentiable there. Okay, problem number 6, if f and g are increasing on an open interval AB, then fg is also increasing on the interval AB. Yeah, this is the first time I've ever seen a question like this. I've not seen any teachers really emphasize this particular concept. So a good counterexample, however, would be, let's say f of x equals x, and let's go ahead and just say g of x equals x. Now, it's most definitely the case that for f of x, well, I mean, here's the graph, right? For g of x, it's the same thing. Here's the graph. So in both of these cases, let's say that this is f and this is g, in both of these cases, the graph is increasing on the interval AB, right? It's totally increasing on this interval AB. And let's figure out what A is. Let's say A is -3, and let's say this is 2. Okay, and we'll kind of do that here. So that's these. But then when you do FG, analyze FG, and I'll call it FG of x, well, that would be x times x, which is x squared. But the thing is about x squared is that that is a parabola. Okay, hopefully my student realizes that that is a parabola. Okay, so this is a counterexample as to why this is false. Okay, it's a counterexample because when you have a -3 here and then you have a 2, well, between -3 and 0, I mean, this thing is decreasing, isn't it? Right? And you know, when you're analyzing whether or not a graph is increasing or decreasing, you're always saying, okay, as the fly, let's imagine there's a fly in the curve, as the fly flies to the right, is he going down or up? Well, as this fly flies to the right, he's going down. So that means he's decreasing. As he flies to the right, you know, after he gets past that x value of 0, well, now it's increasing again, right? But anyway, this is a beautiful counterexample of how this is not necessarily true all the time. Okay, FG is not necessarily increasing on that same interval. Here's a counterexample. So this one was a real doozy. They're being really sneaky with this one because I have this understanding, because I have textbooks and stuff, I have this understanding of the extreme value theorem. And this looks a lot like the extreme value theorem, which made me think it was true at first. But then when I looked a little bit more closely, I saw that they're being sneaky. Okay. So the bottom line is we have, if a function f is continuous on AB, then f attains an absolute maximum value of f of c and an absolute minimum value f of d at some numbers at some numbers C and D in A and B. Now, the tricky thing is you want to notice, well, what's the difference here? Right? It looks the same, but it's different. And the difference is the fact that there's brackets here. So this is a closed interval, and that's an open interval. So this is sort of like, it looks like the extreme value theorem, but it's not. And the fact that this is an open interval means it's not a guarantee that there's an absolute maximum or minimum value. An example might be something like, let's say if you're looking at a line like this, that's between -3 and +3 or something. But the interval that we're including, let's say the line extends, okay, forever. But the interval that we're analyzing is from -3 to 3, but it's not including -3, right? It's not including -3. So we are looking sort of, you know, in this area to figure out, okay, well, is there a minimum or maximum value? Okay, we're looking in that area. I'm going to even shade the area that we're looking at. We're looking there. But think about it. It's kind of impossible in this case to say what the maximum is. I mean, you want to say the maximum is here because that's the highest point, but what point is that, right? Or what x value is associated with that maximum? It's not -3 because -3 is not included. It's almost like you're getting infinitely closer to -3 as you move from the right without actually ever making it to -3. So what x value can you say is the actual absolute maximum on this interval? Okay, so that's why the parentheses throws everything off. The fact that -3 itself is not included means you could analyze points that are infinitely closer to -3 but not quite hitting -3, and therefore it's like a moving target. In other words, there's no actual point that you could land on in this interval that would be associated with the absolute maximum point, because there's always going to be some other point that's slightly higher, you could say. Okay, hopefully that makes sense. It's a little bit of a mind bender. All that same logic applies to this minimum situation here, where you want to say that the minimum is at x equals 3, but remember, x equals 3 is not included in this particular interval, so you're analyzing all these points that are really close to x equals 3, But again, moving target, it's like which x value is the one that we could say it corresponds with the lowest y value in this interval. You can't say it, it's a moving target. Hopefully that makes sense. Now, if that sounded like gobbledygook to my student who is watching this, I totally get that. Probably an animation would be good to explain this, some kind of an animation. But the bottom line is just know that this is an imposter. This is posing as the extreme value theorem, but it's not. The fact that these are parentheses means that that's an open interval. This is a closed interval. This is not the extreme value theorem. If the extreme value theorem, if they wanted to make a theorem about this, they would have said it, right? They wouldn't have done it this way, right? This is a theorem that they know is true, right? This is some weird thing. When f prime of c equals 0, the graph of the function f of x has a local maximum or minimum at x equals c. Okay, so this one, admittedly, I was like, well, why is that false? You know, so this is actually false. Oh, by the way, the last problem was false too. Hopefully that was understood. So this is false. And the reason is because there could be a graph, like let's say the original function, f of x, it could totally be a graph that's like this. Like it goes up, and then there's like a moment where it levels out, and then it goes up again. Okay. And the reality is that the tangent line, the slope, the instantaneous slope, at this moment is perfectly horizontal. So we get, and let's say that that's C right here. So if there's a fly flying along this curve, there is this split-second moment where he's going perfectly horizontal, and in that moment, the slope he is traveling is 0, which is what this is saying at C. But then it goes up again. Now we can clearly see in this counterexample that this point is not a maximum or minimum. So in other words, just because the instantaneous slope at this point C happens to be 0, it doesn't necessarily mean that there's a peak or a valley here. It could just go up again after that. Okay, so hopefully that makes sense. If f double prime of 3 equals 0, then 3 comma f of 3 is a point of inflection on the curve of y equals f of x. Okay, so let's just, for my student at home, just know, you know, the double prime thing, the taking the second derivative is indeed a way of finding out where the original function is concave up and concave down. And, you know, what that looks like is something like this. Like, let's say you've got a curve like this, and it goes on forever. Well, this green part is concave down, okay? And we can say the blue part is concave up, and that point in between is called the point of inflection, okay? The point of inflection right there. You know, anytime the graph changes from concave down to concave up, then you know that we're dealing with a point of inflection. That's like the definition of a point of inflection. It's the point around which or about which a graph turns from concave down to concave up or vice versa. All right. So let's say you've got some crazy function like x to the fifth plus 3x squared minus 2. And let's say we want to take the first derivative of that, and that's clearly 5x to the fourth plus 6x. And then let's say you take the second derivative of that. Well, you would have 20x to the third plus 6. And typically what you want to do, if you want to find the points of inflection on this thing, well, what you would do is you would do a sign chart. You would do this thing where you'd set up a number line, and you would set this equal to 0 and solve for x, okay? And that would be negative 6 over 20 equals x cubed, right? So that would be a crazy number. That's what happens when I make up problems sometimes. So we're looking at literally the cube root of, what's that, negative 3 over 10. Okay, now it is okay to take the cube root of a negative number. You shouldn't be taking the square root of a negative number, but it's okay to take the cube root of a negative number. So I'm going to use my calculator and actually estimate what that is real quick. We're looking at negative 3 over 10 I'm going to raise it to the 1/3 power on my calculator, which is the same as taking the cube root. So we're looking at essentially negative 0.669, okay? Crazy number, but that's somewhere on here. Let's say it's right here, negative 0.669. And typically what you would do then is you would investigate, okay, well, let's investigate this section over here and find out if f double prime is positive or negative. If it's positive, that means that the original function here is concave up there. If after plugging in a test value here causes it to be negative, then the original function is concave down. So I say we go ahead and just try -1 as a test value. And then we'll go ahead and plug that in here. So what happens when we do f double prime of -1? Well, that would be 20 times -1 cubed plus 6. And that's going to be a negative number. I believe that's -14. Okay. So that's negative. So that means it's concave down here. Okay. Now, if I do a test value of 0, and I plug in 0 here, well, that's clearly, you can kind of see already, it's just going to be 6, right? So that's going to be concave up right there. So what we have proven with this sign chart is that without question, there is a point of inflection associated with -0.669. But that makes it seem like, well, then why wouldn't this be a point of inflection? Like, isn't this what I did over here? I basically took the I set f double prime equal to 0 right here. I solved for x. I realized that x is equal to -0.669. So what I did is I essentially demonstrated that f double prime of -0.669 is equal to 0. That's what I demonstrated. That's exactly why I decided to call that my critical value. And then I did a little test value over here. I did a little test value over here. And sure enough, this turned out to be a point of inflection. So why wouldn't this necessarily be a point of inflection? Well, the reason is because occasionally when you do this sign chart, you're going to get your critical values. Like, let's say you get a critical value of -2. There's a critical value there. Let's say there's a critical value of 1. But occasionally you're going to get a concave down, and then you're going to get another concave down. And then maybe over here there's a concave up. So these critical values were a result of setting the second derivative equal to 0 and solving for x. I got -2 by setting the second derivative equal to 0 and solving for x. I got 1 by setting the second derivative equal to 0 and solving for x. So these are definitely critical values, but this one is not a point of inflection because you have a concave down and a concave down. Point of inflection is only when you have a concave up and then it switches, okay? So it turns out that even though -2 was a critical value in this other different imaginary function, even though -2 was a critical value, it turned out to not be an actual point of inflection. And that can happen sometimes, okay? That can happen sometimes. So an example might be something like, the function y equals 1/12 x minus 3 to the 4th. So let's actually investigate that. That could be interesting to see as a counterexample. Why you're going to get critical values, but not necessarily points of inflection. So we have y prime. This would be chain rule. So it's going to be 4 times x minus 3 raised to the 3rd times the derivative of what's inside here, which is just 1. So y prime would be 2 times x minus 3 to the 3rd. So then when we do y double prime, that's going to be 6 times x minus 3 to the 2nd times it's chain rule times the derivative of what's inside here, but that's really just a 1. So we can leave that alone. So let's see what happens when we set this equal to 0. So we have this, right? We have a scenario like that. We're going to divide both sides by 6. That would be 0 equals x minus 3 to the second power. You could then take the square root of both sides. I'm in the habit of saying plus minus. So that would certainly be 0 equals x minus 3. And then lo and behold, you have 3 equals x. So clearly, if I do the sign chart, that's associated with the second derivative, clearly one of the critical values, in fact, the only critical value is 3, right? So let's investigate a test value of 0, and we can investigate another test value over here of, let's just say 6, okay? So we'll test out 0. When we plug in 0 into this, that's going to be 0 minus 3, which is negative 3. Negative 3 squared, positive 9. Positive 9 times 6 is clearly 54, so that is a positive. Therefore, the original function is most definitely concave up. Okay, it's most definitely concave up there. Now, when I plug in a test value of 6, well, look at what happens. It's going to be 6 minus 3, which is just 3. 3 squared is 9, and that's also going to be a positive 54. So once again, we have another concave up. So this is a clear example of how we had a critical value. This is, like much in the same way that 3 was a critical value over here. We had a critical value where f prime of 3 equals 0. In fact, this is a great example because this perfectly aligns with this. We have a critical value where f double prime of 3 equals 0, right? But it turns out that that's not a point of inflection because it's concave up, concave up. Anyway, my student is really smart, so she probably already understood what I'm talking about like hours ago, and I'm probably explaining it like I'm over explaining it. But anyway, just in case, that is the reason. Now you might be wondering, okay, how does that work? I mean, how can you have like concave up and then concave up again? And it's because I think it applies to this one. The graph of this, shifted over 3 for sure. The graph of this, it kind of looks like a parabola, except it like flattens like that, kind of. Okay, and then it goes up again. Now, what does that mean for us? That means that it's totally concave up here, right? And by the way, it's totally concave up here, right? Totally concave up here, concave up here. But because of that sort of flattening action, which I'll demonstrate with this blue line, it got smushed down here. There's actually a moment where it's at this x value 3, there's actually a split-second moment where it's neither concave up or concave down because it's like flat. Okay? Think about it. A flat line is not concave up or concave down, it's just this smushed flat line, right? So there's a brief moment at x equals 3 where it's neither concave up nor concave down, but on the left side it's concave up and on the right side it's concave up. What do you know? Okay, and for the record, we're used to seeing concave up as this, but concave up could be like half of that. That's also concave up, and also you can say concave up is that. And we could contrast that with concave down. Concave down could look like this on a graph, but it also could look like this. It also could look like this, right? So think of the U shape for concave up, and the left half and the right half would still be concave up. Think of the upside down U for concave down in the left half, and the right half would still be concave down. Okay, so hopefully it makes sense why that's concave up and that's concave up. Anyway, hopefully this helps. Short video. Very tricky problems, I must say. Very tricky problems, very abstract, very sort of like conceptual, not very down to earth. It really requires you to understand like the properties and the definitions and all that stuff. So hopefully this is helpful, and I will talk to you later.